I'm going to click open at your side of the computer.
Yeah.
So, all right. Thank you everyone for coming to our last talk of this semester for our Megabyte series. So for those just first time joining us, this is a seminar series hosted by the US ACM student chapter at Berkeley, where we're trying to connect all, as computational mechanics is such an interdisciplinary topic, we're trying to connect people from different groups, from different departments, and so we have this kind of series where we can kind of both know other grad students from other groups, and kind of have a little understanding what their background and what their research interest is. So before we started, can the folks on Zoom let me know if you guys can hear everything all right? A quick thumbs up will be good. Let's see if I can... or anything in the chat. Is everything okay for Zoom, folks? If so, if there's nothing, I will assume hope for the best, and then I'll let Tim. All right, we got a thumbs up.
Thumbs up.
Good,
Awesome.
that's good. All right, that's great. So it's my pleasure to have Tim today from Professor Sanjay Govinji's group to kind of give a talk. We have taken a lot of Professor Steigman classes together and Professor Chopin-Lee's class together, so I'm very excited to hear what interesting things he have been doing. And so without further ado, I'll let Tim take over now. Thank you.
Alrighty. Hello, everyone. My name is Tim Carlson, as Ian has mentioned, and today I'll be talking about both my path to studying here as a PhD student and my research on fully coupled simulation models for energy storage, solid-state batteries in particular. All right. Yeah, so first I'll introduce myself and then go over some research. So, about me a little bit. So, I graduated in 2022 from Johns Hopkins in civil engineering and math, which will become apparent in what I talk about in my research. And then last year, or I guess this year, last academic semester, I graduated with my MS and am now officially a PhD student with Professor Sanjay Govinji, where I study, as I've mentioned, multiphysics models for simulation of battery materials, but also some other things as our interests sort of allow and diverge from this topic somewhat to other things. But mostly I'll be talking about this today. So a little bit about how I came here, how I ended up studying for my PhD in computational mechanics. Well, so I knew in undergraduate that I wanted to be either a structural engineer or a mathematics professor / mathematician. So I actively pursued both simultaneously because I was certain that I would choose one or the other. So naturally, I ended up doing neither because I had a brief stint as a physics major too, and I thought maybe I wanted to be a physicist when I started at Hopkins, but I realized that that work was so esoteric that I might as well just fully commit to math if I was going to go that route. But I sort of realized that that part of me would never be fulfilled as a structural engineer. Like the work is fun and fine, but I think that there's a part of my analytical brain that was never going to be satisfied just doing that. And so the more I learned about the field of, civil engineering, mechanical engineering, mechanics in general, the history, the more I realized that there was something in the middle, which I didn't know early on in my undergraduate studies. And as I became more aware of that, I began to pursue that, more wholeheartedly. And then how I chose my advisor, I think it was either fortuitous or good planning on my part that we have very similar interests, which allows me to sort of exercise a lot of intellectual freedom, especially given that oftentimes when I have some diverging interests from the immediate research topic, they align well with Professor Govinji's. And then it's a very small research group. As a matter of fact, it's just me and a postdoc. And so I get a lot of attention, which I really appreciate. And the nature of my work doesn't really necessitate a large group in order to be efficient, especially because Professor Govinji is so well connected, I can have access to a lot of different experts and then my colleagues in the department without being in a large research group myself, which I really like. And then where I hope to take this, when I'm learning the degree, when I'm done. So I've been fortunate enough to be able to work with the Abacus team over internships and through some continued consulting as well throughout the semesters, which has been very fulfilling personally and would not have been possible without my studies here. This is something I would not have had the opportunity to do had I just either, finished with my master's degree or never gotten to grad school to begin with. So that's something that I think I owe to Berkeley. And on top of that, moving on, whether it's as a professor, working at a national lab, or working at DS, I think that those are the kinds of things I want to do. Anything that allows me for this sort of intellectual freedom I have here.
Yes.
Oh, Gestalt Systems is the company that bought Abacus. Yeah, I should mention that. Abacus is what we all think of, but technically it's owned by something else. And that's what I would be working for after the fact. But I just want to do something that aligns with my interests. And through the work I have been able to do there, I've come to understand that that would align with my interests and give me the intellectual freedom I desire. And the ability to work on difficult problems such as solid state battery multiphysics, which now we'll get into. So, as a brief introduction to the topic, as you all may be well aware if you've seen the news in recent years, liquid electrolyte lithium-ion batteries are nice and they're good, but they have their problems. Most notably, among many, is that they are highly flammable and unstable, as a matter of fact. And that instability not only makes it more difficult for the general public to adopt these technologies that are, all things considered, still more sustainable than, say, petrol vehicles, it limits the ability to adopt them. And then there's other considerations beyond just the flammability of electrolytes. Technically speaking, liquid electrolytes are sort of at a limit. They're not getting any more effective. All advances in liquid electrolyte technology and liquid-based lithium-ion battery technology has sort of stalled or all but stalled. And then on top of this, there's other considerations for sustainability. And while you think, oh, batteries are sustainable, well, there's other ways to view this in terms of the fact that, for example, cobalt is heavily used in lithium-ion batteries. And cobalt mining is, well, highly problematic to say the least. There's a lot of unfair labor practices involved in that, criminal by our metrics. And so as a proposed solution to all of these problems, solid state batteries sort of offer a viable alternative. It's not necessarily the case that they need the same materials. It's certainly not the case that they use the same electrolyte. The solid material is non-flammable. The worst thing that can happen with a solid state battery is that it will break, which is much better than risking death because of your battery failing. And on top of those benefits, there's the incredible benefit of the most promising materials offering upwards of 10 times the energy density of modern state-of-the-art liquid electrolyte batteries. So you get from, let's say you have a car with a 300-mile range. Instead of driving up the coast of California, you can now drive across the country on one charge. And on top of all of this, you have improved stability with no flammable components. And now every time I give a presentation on batteries, I'm reminded that I should explain how they work. So I'll do that very briefly. So basically, during the charging phase of a cycle, you have lithium that goes from a stored state intercalated in a cathode material. We'll say, because they're not labeled, we'll say that the red is the cathode. It goes from the cathode during the charging state to an anode material, where it then either intercalates into the anode material or plates on top of it. So the plating would occur as the preferred method of charging in, say, lithium metal, where that's really the only option. And so, yeah, during charge, lithium goes from cathode to anode and then back again based on this happens because you're putting the system out of equilibrium by imposing a potential difference, which then induces a current. But of course, we would already have these technologies if there weren't issues with them. So the improved stability that I hint at has not yet been realized. They figure, oh, there'll be better stability in terms of dendrite growth and crack or dendrite growth, electrochemical stability. But the main issues now for solid-state batteries are chemomechanical instability at interfaces. So what happens is that dendrites grow into cracks or grain boundaries of materials and cause fracture within materials, or even just grows through grain boundaries and eventually causes a short circuit within the solid-state battery. So this sort of instability has not been solved, and because of this, current solid-state battery technologies need to be run at such a low charge discharge current that they can't be used in the kinds of applications that we need them in an efficient way, such as electric vehicles, at least not the most promising materials. What you're hearing about is something like 3 times the capacity at most. For like, what I mean by what you're hearing about is like, say, from Hyundai. They say they're going to have a solid state battery. That's going to have maybe 2 times the range because they can't yet use the materials that would give them that extra boost to, you know, something that would completely replace gas vehicles just by virtue of being that much better. And so basically there's universal agreement in the literature that the existing models cannot adequately account for all of the different factors going into why these materials are failing, this failure is highly coupled. These current concentrations occur due to simultaneously electric field concentrations, sources and sinks of actual concentration of lithium, and of course, stress concentrations. All of these things together with added effects of differing temperatures, et cetera, lead to this sort of instability. And you need to be able to look at them. You need to be able to look at the problem holistically, or else you won't be able to get it right. And moreover, something you'll notice, this is a nonlinear theory that we're developing and trying to implement. That's really important because it's been shown, it's been proven that even in small deformation cases, the shear strains in particular that end up leading to failure cannot be properly modeled in a linear theory. It's been shown that you get upwards of 2 to 3 times the shear stress just by accounting for nonlinearities in the deformation. Should almost be expected because the amount that these batteries swell, so silicon swells 300%, but lithium swells about 5%, and even that's exceeding the range of the linear assumption. So we need to solve this instability issue. And so pretty recent, like past 2 years, experimental evidence with experimentalists playing with the magnetic field, playing with batteries in a magnetic field, has shown that cyclability, so the ability to charge and discharge a battery without losing any capacity, is greatly improved. The interface is all but completely stabilized if you orient a magnetic field perpendicular to the battery. And what that means is if you've got like anode, cathode, you want your magnetic field to go through. So think center of a solenoid. But if you've ever done any sort of electrodynamics or anything, you know that once you have the magnetic field involved, things get very, very complicated very, very fast. And this is no exception. So there is no continuum theory currently that can account for everything we need to account for, that being the chemistry, the thermal effects, the electromagnetism, and of course, sort of key to all of this, the stress. Until now. But why is this? Why is this so hard to do? Well, there's quite a few reasons. The first and foremost, maybe the most obvious, is that mechanics and thermodynamics are Gallet invariant. So rotations at constant speed, if you rotate your frame of reference and you're moving at a constant speed, you should expect to see the same result if you're looking at a system. That is not the case for electrodynamics. In electrodynamic systems, you actually have a phenomena where if you're moving relative to, let's say I'm looking at something and someone else is moving relative to me, we'll both look and see two different states of charge, two different magnetic fields, two different electric fields. We'll see two different things. And that's because in 4D, the electromagnetic field is more like a tensor, second order tensor, than it is a vector. In reality, when physicists look at these fields, that's what they look at. They look at a second order antisymmetric tensor, not a vector. And it's second order because in 4 dimensions, you can look at it in terms of an extra time component. And when we look at it in 3 dimensions, we completely lose the ability to do that. And so this adds a lot of complexity. It sort of violates the quote unquote principle of causality. In electromagnetics, you can have such a thing as reverse causality. If I know the charge and current in the future, I can actually compute the fields now, which sort of violates what we think of when we think of how cause and effect work. But in a relativistic setting, there's no problem. The principle, quote unquote, of causality does not apply to electromechanics or electrodynamics. And so all that to say, this is a complicated theory, and a lot of people will make mistakes trying to interpret it correctly. The physicists have it all figured out, but in order to read that writing, you need to be able to read the writing, which is not easy. But anyway, so in order to propose a well-formed theory, you need to restate electrodynamics in a Galilean invariant way, which involves sort of introducing a velocity as almost a state variable, as something that is intrinsic to all materials. And it's like a velocity relative to an electromagnetic rest frame, where we sort of declare a rest frame and then associate a velocity with each material point. And so that way we get a velocity relative to a known quantity. And once you do this, you can actually create Galilean invariant for the electromagnetic fields, which sort of captures that 4D effect by including the velocity. And you're able to create a theory that's able of describing these materials in a Galilean invariant way. As a consequence, you get some weird things that happen. For example, there's a heating in electromagnetic systems that is not heating in the way that we usually think. It does not contribute any entropy to the system. The reason we consider it heating is because if we didn't, we lose Galilean invariance in the power supply. Basically, the power supply of the electromagnetic field to a material is this current dot electric field quantity. Neither of those quantities are Galilean invariant. So the way we reconcile this is by constructing, through these constructed Galilean invariant quantities, where we have a Galilean invariant electric field, math blackboard E here, E plus this magnetic field term, and a Galilean invariant current, you can separate the two. And this Galilean invariant current is actually precisely the conduction current. And so you end up getting this J dot ES as a heating term, even though it's not a heating, it's just a method of analyzing the system in a invariant framework that corresponds to our other sense of invariance without violating anything. So it's just sort of a remnant of the fact that we're trying to look at this theory in a different way when it's really Lorentz invariant. And so another tricky thing is that in their usual form, Maxwell's equations are dependent. So if you just count quickly, we take I and Q to be known. There are 6 equations here, or 8 equations, because there's 2 vector equations and then 2 divergence equations. So 8 equations, 6 unknowns, with the 8th a relation. So H is related to E via a constant. Or not, H is related to B via a constant, E related to D via a constant. So these are Maxwell's equations. We have 6 unknowns, 8 equations, it's overdetermined. This isn't really a problem, but you get very high order derivatives if you reconcile this. But if we introduce a potential for E and B, which is very simply justified in the 4D case, but I'll skip over that part. It's you can get it via Helmholtz decomposition theorem as well. But basically, introducing this, we reduce the number of equations and unknowns. We have a determined system, 4 unknowns, 4 equations, but we introduce gauge freedom, which, to overcomplicate it, it only determines A up to a cohomology class. To bring that back down, it basically, in 3D space, determines A up to a scalar function. But we can ignore this by imposing a gauge, and then in an FEA setting, we can satisfy this automatically by what's called the Coulomb gauge. We say the divergence of A is 0. But this introduces another problem in this particular case, because our system is not so complex or so simple as to be able to say, well, we know J is going to be, or the current is going to be in the curl space. We can't say that. We don't know, but especially because the only thing that suggests that the current will be divergence free is this equation in principle. Without that, it merely could be the case, which in an FEA setting means that if we use the typical Bubnov-Galerkin approach, we may end up solving the wrong problem. And what that means is that we might end up finding a system where this curl A minus constant times the current is some gradient and not 0. We want this to be 0. If we limit this variation of A to be in the curl space, there's no way of guaranteeing that this is going to be what we want, which in a very simple case, for example, a simple just electromagnetic problem, this isn't a problem because we're simultaneously, let's say V is 0. We're simultaneously solving the Poisson equation. Or actually, in this case, the Laplace equation for the potential. In that case, we can say that J is actually proportional to the Laplace of, or J is proportional to the gradient of the electric potential. And in that case, we actually end up solving, or we do end up in a situation where J is in the curl space, as we can say. But in the general case, in an electrochemical case, we are not so lucky. We don't know what that is. We need to enforce that the divergence of J is 0 somehow, or else we have a charge distribution within the material, which is totally non-physical. We're solving the wrong problem in that case. It could be the case that all of the equations we pose are solved, but this equation does not satisfy it doesn't satisfy the strong form, so it doesn't imply the strong form, which means that we need to use a Petrov-Galerkin approach in order to solve this, where we use different equations for A, or the variation of A, in order to solve the problem, in order to impose a stricter condition on the residual. And so finally, I'll touch on why a referential electromagnetic description is actually favorable here. In some cases, people have used, in similar problems, like say like Eulerian mesh for the electromagnetic field, and then a Lagrangian mesh for their material, or something similar, some ALE method. Well, here, accuracy at the interfaces is of the utmost importance. We need to get that right. Minimizing interpolation there is pretty critical. And then other fields, for example, chemical, all of those equations are in reference to, like, what the constitutive equations should look like are always in reference to a reference concentration, not the current concentration in the current configuration, the concentration with respect to a reference configuration. That's how the Butler-Volmar equations, which govern exchange at interfaces in electrochemical systems, that's how those are posed. So if we can't know the reference concentration, or concentration with respect to the reference configuration, we can't solve the problem. So certainly one thing needs to be Lagrangian, and then because accuracy of the electromagnetic fields is so important at the interfaces, that should also be Lagrangian if we can. Also, there's like 9 to 10 degrees of freedom per node. Just making this as simple as possible is also very important. Make this efficient. And also, if you do this in a Lagrangian framework for everything, in the case of a moving body, the equations are actually much simpler. And so basically, sure why I have these on the same slide, but after you apply the Coleman and Noah argument, you end up getting to these equations where you can see how the couplings become manifest. We want to show, the whole goal of this is to essentially show and enable people to be able to study the effects of a magnetic field on a battery. And it's evident, so A is the magnetic potential, magnetic vector potential. Its rate of change is, could be, especially for the current, a very important factor in determining the actual field. So it's manifest how the couplings occur for one, but also most importantly to this application, how the coupling to the magnetic field looks. It's direct. And this is the referential form, by the way. That's where all the F's and stuff come from. You can ignore the F's and the J if you want to think of the spatial form of this. And so just to give an example of what these end up looking like for real material. So for LiPon, lithium, phosphorus, oxygen, nitrogen, there's referential constitutive equations. So we start with a Helmholtz free energy in this case, because the material does not depend on the concentration of lithium. It's fixed, actually, in these separator materials. And so from these, we can recover some constitutive equations. And this is based on a thermoelastic neo-Hookean, adjusted to include electric effects in a way that does not make it piezoelectric, along with giving it the chemical potential that we expect from this material. And chemical potentials usually do not depend directly on the magnetic field, although you could always append terms in order to add some sort of dependence. And so following the whole Coleman and Noah argument, but not actually following it, you can eventually show that these are the case. And basically P is your polarization. You get a polarization that is, this basically says that the material is a linear dielectric, which we expect. Get an entropy expression, you get a stress expression where the dependencies on the thermal part and the electric field are evident. There is an electric field dependency in the stress here. And it is such that it cancels the part that is determined by the polarization in the Maxwell stress. The Maxwell stress is a stress tensor that owes itself to electromagnetism being a part of a system, and it's not a part of the or in this case, second Peele or Kirchhoff stress tensor. So you end up adding those two together in the end, and what you get is like the total effective stress tensor. So the electric part here cancels out the polarization part, making this into a material that is not a piezoelectric. So the total effect of the Maxwell stress on the material ends up being due to the free charge alone. And then you get the chemical potential that is expected from the literature out of this function for this material. And then from these, you get the most interesting part, in my opinion, the transport equations, where, again, both the chemical transport and the electric transport, I being the current, J being the mass flux, both depend directly on the rate of change of the magnetic field, which is not something seen in any like existing framework to study solid-state batteries. So it's evident that if you have a magnetic field in your material and you're accounting for it, it will impact the mass flux, the current in the battery, which is exactly what we're trying to show. We're trying to show that the current in a battery is improved favorably. And by that, we go back to say how exactly we want it to improve. Basically, if you've got imperfections at the surface, normally what happens is you get these massive current concentrations at the tip of these dendrite materials, or dendrites in these materials. So those are just growths at the tip of the, or the surface of a material, where you see current concentrations, and it's sort of a vicious cycle where you have current concentrations, it grows the dendrites, makes even more extreme current concentrations, and eventually you have a sort of short circuit. What happens with these magnetic fields in, this is what they postulate currently, and what they see sort of backs it up as what is happening in the material. When you have a magnetic field, if the current tends to diverge towards a dendrite tip, magnetic field in principle should pull it back on course, because the effect of a magnetic field on a moving charge is basically, if it's in line, there's no effect. If it starts to move out of line, it starts to change the direction of the charge. So in principle, and what is postulated to be happening is that when current comes down to the surface of the battery, a micro MHD effect happens around these dendrite tips, which causes more uniform plating than just at the tip. It plates around these dendrites and effectively smooths them out. And so because of the magnetic field, you're able to smooth out the interfaces, which improves stability massively, just by changing the direction of the current. And that's what we're trying to show analytically, which hasn't really been shown in a simulation model. And that's why seeing the interrelation is so important here, because you want to be able to prove that the magnetic field is substantial, which whenever you're working in this sort of complicated system with the magnetic field, that's sort of step one, is proving that it is necessary to look at before overcomplicating the system further. So as far as next steps are concerned, the one that's most immediate is just finishing the development of some elements in FEEP that are capable of just simply describing the electrochemical magnetic effect to show if you have this applied magnetic field, you will see improved performance for, compared to a situation where you don't, which justifies the inclusion. And then after that, develop a fully coupled model to then see, okay, now that we're looking at this, now that we know we get better effects, how do the stresses at the interface compare? Because we also want to show that when this improved performance happens, you do not expect to see as much or fracture in the same way. You hope to stabilize the interface mechanically, because right now that's the biggest problem. And then once we're able to do all that, we need to revisit the material models and then account for actual evolution of the materials. So plastic, viscoplastic in the case of lithium metal, and then explicitly model growth and degradation of the materials, because we want to be able to very explicitly show, not just by some toy swelling model in lithium, which is totally non-physical, we want to be able to explicitly model plating. And for this, in order to do this efficiently, I'm toying with a lot of ideas with how to do this, one of these being this fun little pseudo-domain inversion thing, which I made up, where you can inject or immerse, more accurately, a reference configuration in a larger subspace, deform the larger space, and then embed or submerse the larger space into a real current configuration, which allows you to map diffeomorphically to a fractured configuration from an unfractured configuration. So you make a discontinuous phenomena continuous. Essentially, how you do that is by changing the topology of the original configuration smoothly. And so it's this idea I have of trying to efficiently model fracture without any extra fields. But there's a lot of work to be done there. And that's basically it. So thank you all for your attention. If there's any questions, happy to answer.
So are there any questions from the folks in the audience and folks on Zoom? If you have any questions, just kind of unmute yourself and kind of just ask, I think. Is you're unmuted? All right, I guess.
Let me see.
Question?
Maybe it,
There's a question in the back?
Yeah.
Works. I guess.
three questions. So first one, you simulate your magnetic or do Maxwell equations, and then you have another system which is Cauchy balance something, right?
Mm.
Are you solving them fully coupled or?
Yeah. Simultaneously, fully coupled. Yeah. So one large stiffness each step.
Well, that's a lot of degree of freedom.
Yeah. That's why there's a lot of consideration made to trying to do it. Yes, it is necessarily transient. So we assume quasi-static as far as the mechanic case, but all other fields are allowed to evolve transiently.
Like I know this is a little bit too much for this stage, but when we have static, right, considering that the strategy is Cauchy balance algebraic system as well, which is
Yeah. Probably Rungakuda, but like I think that it's I need to look at some literature involving. I think most people use Rungakuda for this sort of problem, especially for the Maxwell equations. Yeah, of course. Yeah, implicit for sure. There's never the explicit would not be possible with this, at least to any degree of accuracy.
But why do your function model the explicit? Any idea of that?
Oh yeah, that's a yeah. So that's sort of what I'm trying to figure out. My goal is to yeah, I need to figure. I want to figure out how to try and do an implicit fracture time stepping.
Yeah.
Which is part of this whole like pseudo domain inversion idea. I'm trying to figure out how to continuously deform a discontinuous phenomena. Yeah, I'm trying to avoid the extra field. That's really the only reason I'm hesitant to use phase field. Yeah, I can probably use phase field. You're right. At the cost of another degree of freedom, which if I can avoid would be nice, but I'm trying to figure out a way to. It sounds like almost impossible, and maybe it is because I haven't. Mm.
Probably just easier. That's
Yes. Yes. Yeah. Yeah. It's costly. The other.
Is this the point where we just get a high performance computing and we just start blasting it?
Oh yeah.
On the electricity.
I just got a new desktop with 198 gigabytes of RAM, so I'm ready.
We're needing this one right there.
Exactly.
extended finality.
Yeah. Oh yes. Oh no, that's a colleague of mine. Yeah. So I don't know. I think that phase field is probably the most promising. But another reason I'm not the biggest fan of phase field is just because so much of the most important aspect of what's going on is at the interface, at the interfacial nodes, which I do not want to smooth in any way. So we'll see.
Yeah, I prefer for Facebook because we need really much smaller mesh, and I think you have costs like
Oh yes.
I mean the Facebook requires like a well-defined gradient, so
Exactly. Yeah. Yeah. Exactly. That's kind of what I'm saying. Is like if I'm smoothing a coarse mesh at that interface, it's like
or
yeah.
alternatively probably use like a XFBM or like so maybe like enhanced or whatever enhanced.
Yeah. Yeah.
I tried adaptive meshing strategy on the track something.
Yeah, at the interfaces. Yeah, that's a possibility. Yeah. Yeah. That's a good option. Thankfully, I don't need to worry about that for a couple months, but eventually I will. Eventually, yeah. Because that's one of the most important like end goals, like, is to eventually have fracture in this model, which is going to be a challenge.
So going to your last kind of idea about the whole spaces, so I'm just kind of curious about how you're interested in, can you give a little more information on what you meant by the whole modeling, discontinuity, singular surfaces without, explicitly putting it. Are you trying to extend these functions, these discontinuous functions so that it become like a bigger space?
Yeah.
Mapping and so you're pretty much going for like kind of Kovinsky sort of just having a bunch of extensions, or are you just trying to bake that in for like some sort of, jump condition that we see in fluid?
Yeah, no jump conditions. I'm basically trying to extend the domain, and then essentially what the boundary conditions will end up looking like is some Robin type condition that ends up being automatically computed in such a way that you would get the same boundary condition at the real boundary, but you're solving it at a larger or different boundary. So in this case, like in the case of fracture, what this extended domain would look like, and analytically this works, but I have no idea how it would work computationally yet. What your extended domain looks like is the coproduct or disjoint union of the space that you're analyzing with itself. And so what you end up having is like, you're essentially solving the same problem twice, but only on like, so you end up solving the same problem twice with boundary conditions applied, say on one half, and then on the other half in the other one. And then you end up injecting the solution from both, from the domains that you want, or from the subdomains of each one that you want into real space to get the actual solution. So you sort of are solving the problem twice, but you're solving a simpler problem twice.
Space is split, disjoint union, one side is fracture, so that's the discontinuity you have there, and then you're okay.
Yeah, so you end up solving a continuous problem on both spaces. The submersion into the real domain is continuous and locally invertible. And actually, since the disjoint union has the same dimension as the original one, it actually maps as a local diffeomorphism. And so you're able to both go in and back continuously. Exactly. You're able to go in and back continuously. What ends up happening, why that's possible, it sounds counterintuitive. The reason why it's possible is because what you're really doing in this effectively is changing the topology of the original space with each iteration. So every time you're, so whenever you're like, let's say you have these two disjoint, like this disjoint union, whenever you have, say, any differences between the disjoint union, what effectively happens is that you're smoothly changing the topology of the original space, which is sort of it's interesting analytically, but if it'll work in simulation, I don't know. Yeah.
I got this question is that you say you're going to do everything Lagrangian, right?
Yeah.
Something like total Lagrangian, or you're doing adaptive Lagrangian.
Total
Lagrangian. So you have extra Lagrangians for these variables.
Just do it with that.
Just to pull back. That's why. Yeah, that's why having this diffeomorphism is so important, because if you don't have this, then this is impossible.
This is just second. The topology of like price change steps, but what you want to do is basically try and introduce discontinuities into all. I'm not sure many people have looked at this, but
I haven't seen it.
Yeah, I've seen people do contact. Contact is a bit similar, but what you can do is that when it's just touching, right, and just activate a flag that basically you are right now connected. But maybe what I'm trying to say is it's the other way around, right? Like you have contacting bodies, and then when there's a discontinuity, there is a flag that basically says that, okay, you are not like, I'm not interacting with you anymore.
Yeah, essentially.
Lagrangian attributes like inequality.
Yeah. And the reason why total Lagrangian is so important is, again, because I need that J from the original configuration. Yeah, or else I can't solve for the chemistry.
useful, easy, but it's tricky because it's inaccurate
Mhm.
in many ways. Total Lagrange is probably bad.
Yeah. Yeah.
And also, like, you need to, like, when you do the electrodynamics, you do like also in total Lagrange or like the other piece.
No, I'm doing it Lagrangian. So that all the electric fields, electromagnetic fields are pulled back. Yeah.
It's always right there.
Oh, there's no plasticity.
For now there's no plasticity, so total Lagrangian is easy enough. Yeah.
Sort of like try to like just even without cracks and everything, like this swelling to 5% stuff. I think I've seen like people try to sort of like simulate this expansion.
Yeah.
You like try to do like I mean, I'm not sure whether your development has been to like a validation stage, but I'm just curious that try to check that.
Oh, I haven't gotten to that stage yet, but that's like
That's like
this probably this month. Yeah. I'm very close to being at that stage. But
that's the only equation for this thing.
I know, yeah. Yeah. And I mean what I'm really gonna be comparing against is like the abacus implementation of this. Like without the magnetic field, it should match the abacus implementation. I'm hoping. Yeah, so they essentially solve all of these equations that I'm like, so if I neglect temperature, neglect deformation, then and magnetism, of course, they essentially have exactly this system implemented. And so what I'm going to do is essentially apply everything, just essentially boundary conditions for magnetic field are just 0 to Dirichlet. And it should compare very close to their case, and then have a non-trivial magnetic field boundary condition, and then hopefully I see some important differences or non-trivial differences. And that's sort of how I'm going to validate. They have theirs validated. And then after that, validation is going to be a bit ad hoc because it's going to have to be against experimental data. The interesting about this problem is that so there's some talk I had with someone else about using AI to solve this. That's impossible. This problem has like you need to get over the barrier of like knowing what the solution looks like before you can use AI, which no one knows what the solution to this problem looks like yet. So
They use very expensive experiment.
exactly, it's just not possible. And so exactly.
So they would need cameras to tap the cracks, and then they need depth sensors.
It would cost billions.
They'll have a bunch of coils around that lithium.
Oh my God.
What to scan this like microscopically at like every times, right?
The current data that they still have a bunch of lures that are
Oh
sitting.
my goodness, yeah. There's so much.
How much does one of those cost?
Like $30,000 at least.
Like,
Yeah. And I mean the materials themselves are not cheap too. And you're going to need like hundreds, if not thousands, of samples, destroying them at it's impossible. And the thing is, no one has successfully run one of these batteries. So basically, I'm comparing, like, once I get to a certain point, I'm comparing against nothing. Like if I were to successfully show, oh, this chemistry is stable, it's like, okay, what do I compare against? It's interesting. It's like the simulation has to stand on its own. I have to get someone to validate it. Thankfully, there's people here that do that kind of thing, but otherwise it stands on its own.
so on that note, I think we are right about time. I have 1 more minute left. So I guess we would like to, thank Tim for coming today, and I think great discussion. So that concludes this series for this semester. Thank you, everyone, and thank you, Tim, again.